Hi guys, in this video we're going to go on with graphing rational functions. The first step to graphing a rational function is to set the denominator equal to 0 and solve for x. And the reason we do that is because then I know, like in this case, that I'm going to have a vertical asymptote at x equals 2, and I know the domain is that x can't be 2. The second step is to compare the degrees of the numerator to the degree of the denominator, okay? And the reason that we do that is because it deals with the horizontal asymptote, as you could probably guess from the table over here, okay? If I were to go through, and let's just do this with basic functions, okay? We're going to start having x on top and bottom of the function. And so if I go through and I look at the degree, remember degree means the highest power of x. So I'm going to rearrange, I'm going to find which one's the highest. So even if it's like x squared plus x cubed, the cubed is bigger. So it's a third degree function, right? And so if I end up with something like, let's say, x cubed over x squared, what we're interested now in, well, first of all, x can't be 0 because that would be dividing by 0, right? So that would be like the part of the step 1 business that we're doing. But what else it tells us is this. See, if I put in a, let's pick some big values of x out, right? Like maybe 10, okay? If I put 10 in for x, then I'd be talking about 10 cubed over 10 squared. And by the way, that does reduce. It's 10 times 10 times 10 on top and 10 times 10 on bottom, right? And I cancel out a lot of these. I'm left with 10. You know, that would be 10. So if this was my equation here, and I said I wanted to plot some points here and I wanted to graph it out, if I put in the x coordinate of 10, so I'm talking all the way out here, right? I'm going to be 10 is going to be the location of my coordinate, okay? So if it's y equals x squared, I put a 10 in for x, I get 10 for y. But what happens if I put 100? What do you think 100 cubed over 100 squared is? Well, it turns out that that ends up being 100. So if I put 100 in for x, then I get 100 for y. Just like if I put 10 in for x, I got 10 for y. And guess what happens if I get 1,000? Well, I'm going to get 1,000 out. And if I put 1 million in, I'm going to get 1 million out. And that means that my graph, if I were to look at it, that graph is going to grow. It's going to grow and grow and grow, and it's never going to stop growing, is it? And what we're saying here is as this thing grows, okay, as I look at this function, that the top grows faster than the bottom. Okay? The top grows faster because it's a cube and the bottom is a square. The top grows faster than the bottom. Why is that important? Because if I come up here and I look at this, I see that the graph that we were talking about earlier levels off, doesn't it? You see how this goes off and it levels out at 0? This thing goes off and it levels off at 0, and I have a horizontal asymptote. What we notice here is if the top is bigger, it doesn't level off. And so what that means is when we talk about where the horizontal asymptote is, okay, so notice here's what I have. X raised to the a power, x raised to the b power. If I'm going to compare the powers, okay, that's what I'm doing here, comparing the powers down here. If the top power is bigger than the bottom power, so like this is x cubed over x squared, right? What we notice is that it grows continually, and I have no horizontal asymptote that appears because it never levels off. The horizontal asymptote is that idea of where does it level off to. Okay, so what happens if I have like x squared over x squared? Or maybe it's just x over x, right? What if I had y equals x squared over x squared? Okay, it's the second situation. This time they're the same power. What I would notice is this: if I have 10 squared and 10 squared, well, that reduces down to 1, doesn't it? How about if I had 2x cubed over 3x cubed? Okay, well, this stuff would go away and I'd be left with 2/3. What if I had x to the 4th plus 2x cubed over 3x to the 4th? Well, see, here's what we're talking about. If I have a billion, if I'm going to put in a billion for x, it turns out that this is the only thing that matters. The x to the 4th just dwarfs the 2x cubed when I put in a billion for it. This thing is so huge that we really don't care. It's like taking a really huge number, like $1 million, and adding a penny to it. Who cares about the penny, right? We only concentrate on the very first value, and I would notice if I'm just comparing the x to the 4th that it kind of just goes away and I'm left with like a 1/3, right? And so what happens is if you went and graph this, what you would notice, okay, is that line that it levels off to is always going to be just the coefficients of the number in front of the first values, okay? I'm going to say y equals, and I need to add some values in here. So let's throw a number in here. Let's say that this is, or letter, sorry. Let's say this is m and this is n, okay? So in other words, like I'm having 2's and 3's out in front. 2 would be m, 3 would be n, okay? All I have to do is cancel out those things in front of this, and the fraction that I have that's remaining is where my horizontal asymptote is going to be. That's where it's going to level off to. So it would have leveled off to 1 in this case because it's 1x squared over 1x squared. It would have leveled off at 2/3 here. It would have leveled off at 1/3 here. That's if the powers are the same. The last situation we haven't talked about is what happens if we have like x to the 4th over x to the 5th. In this case, we have the power on bottom is bigger, right? So the top power is less than the bottom power. Well, in this case, what we notice is that the bottom grows faster, right? And if the bottom grows faster, if you put in like a million, okay, or 100 even, that would be 100 to the 4th power over 100 to the 5th power, right? And so I want you to notice then that would equal out to 1/100th. Man, that's like almost 0. You know, if I put 1,000 in over 1,000 to the 5th, that'd be 1/1000th. Man, that's really that's close to 0, isn't it? And if I put 1,000,000 in, okay, you can guess where this is going, right? If I put 1,000,000 over 1,000,000, million to the 4th, million to the 5th, that'd be 1/1,000,000th, right? And so what we notice is that's the situation where this thing is just getting darn close to 0, but it's never going to hit it, okay? If the power on top, in this case, there is no x, and the power on bottom has x to the 1st, there's a higher power of x on the bottom, it's going to level off at 0, just like our parent function. And so it's always going to be y equals 0. This is a little table that you want to memorize because this is going to be a big deal for the rest of the chapter, okay? What happens if I look at the powers of x on the top and the bottom? Where is that thing going to level off at? Now, I do want you to remember you have your graphing calculator, and so as we go through these next problems, you know, if all else fails, just graph the thing, look at the picture, copy the picture down, and try to use the picture to help get the correct answer. Hopefully this makes sense. In the next few videos, I'm just going to be working through some problems that'll go a lot faster than these explanatory videos that I've made so far.